Okay, so for the second half of chapter 6.1, we are going to cover projectile motion, but first we have to re-talk about velocity. So some of these things you have discussed in your notes. I'm going to go over them in more detail here, go over some example problems. And yeah, so remember that velocity is speed with direction. Right, that's important. So that makes velocity is a vector. Okay, so velocity, speed with direction, and velocity is a vector. So now when we talk about objects moving in two dimensions, right, we got an up and down and a horizontal. Things can move in, so we have a ball here, it can move in a curved path. Now it could be moving at the same speed, but its direction is going to be constantly changing. So this means its velocity is constantly changing. So this black line represents the path of the ball, while the purple lines represent the velocity vectors. Okay, so that's the speed and direction in which the ball is moving. Okay, again, speed and direction is crucial for velocity here. To have velocity, you need a speed and also direction. So speed is your magnitude, right? So that's going to be the number portion. That to get the speed, you need both the horizontal velocity and the vertical velocity. So if we have a ball, if we have a ball that's launched, okay, in that direction with a speed of 5 meters per second. To achieve that speed at this launch angle, okay, right, this launch angle, that means it has to have a very specific vertical velocity and a very specific horizontal velocity, okay? Right? So it turns out, for something launched at this speed with this particular angle, that specific angle will be 37 degrees, but that's not important. You would need a x velocity of 4 meters per second, and you would need a y velocity of 3 meters per second, right? So this was a 37 degree launch angle. Okay, we're not all into trig and angles, so I'm not going to stress on the angle portion. So to launch this ball at 5 meters per second of speed at 37 degrees, that means it would need to be moving 4 meters per second in that horizontal direction and 3 meters per second in the vertical direction, right? So up and down is 3 meters per second, and horizontally, left and right, it is 4 meters per second, okay? So what these things mean right here, box them, okay, these are called subscripts. Okay, these are called subscripts. They help specify exactly what type of velocity we're talking about. So if you have a y, right, next to your velocity, Vy, that means velocity in the y direction. Okay, if you have Vx, that means velocity in the x direction. So if you remember or talk about vectors from previous lessons and then before spring break, these are your components, okay? Your y component of your velocity and your x component of velocity, vx, vy. All right, so if we made that a little bit bigger here. So if we have a velocity vector like that, that means it's going to have an x component that'll look something like that and a y component. Okay? And you could do it the opposite way. So you could draw, so say we want to launch something with this amount of horizontal velocity. We'll write that in up here, Vx, Vy, Vx. So say we gave something, I'll even draw the ball in here. We launched it to the right and gave it that amount of horizontal velocity. And say we gave it this amount of vertical velocity. So this is your x component of velocity, this is your y component of velocity. That means your ball would travel in this direction. Okay, your ball would travel in that direction with some amount of speed and at a certain angle here. And, for those of you in higher level math, you would be able to figure out that angle, but that's not the scope of this course, okay? So one more thing to note, when we're talking about vectors, they have a special symbol, okay? So the symbol, as you may have seen in the previous lesson with displacement, some of you asked about it in some of the classes, they're designated with a little half arrow. So when you're talking about vectors, any type of vector, they get that little symbol, right? So some people will write speed as just a v, right? If you're just talking about speed, so no direction, so the magnitude of your velocity vector is sometimes just written with a v. Then when you're talking about the vector, it's written with a v with the half arrow above it. This is the vector symbol, okay? That separates something from being a vector versus not being a vector, okay? So moving on here, we're going to do a couple examples. So let me move this up here. Okay, so let me just scribble some of that out. Okay, so we have a train right here. We have a train moves at a speed of 100 kilometers per hour heading east. Okay, we want to write its velocity vector in xy form. Okay, so how we've been writing our velocities. So we see, okay, I'm not going to be able to do that. Let's do this. So we got its speed, 100 kilometers per hour. And we have its direction, 100 kilometers per hour heading east. All right, so remember, east is horizontal, so that's our x direction. East is also positive. Okay, so if we were writing our velocity vector, that would simply be 100, comma, 0. So this means our x velocity is 100 kilometers per hour. We can write that over here, kilometers per hour. And our y velocity is 0, right? Our train isn't, flying through the air. It's staying on the track, so it's got no vertical velocity, thank God. And our horizontal velocity is 100 kilometers per hour. So letter A here. If you have a race car moving with a velocity vector of 50, 50 meters per second, sketch that velocity vector and calculate the car's velocity. So you'd have to use the Pythagorean theorem. If you don't know what that means, that's fine. we're just going to sketch the vector here just for fun. So let's do our green components here. It's going to be letter A. So that would look something, say we'll make every block worth 10 meters per second. So 1, 2, 3, 4, 5. It's about 5. And 1, 2, 3, 4, 5. All right, so we have our Vx equals 50 meters per second. Vy equals 50 meters per second. So then, if we wanted to calculate and all that, we could do that. But what this essentially means is this is what our true velocity vector would look like. Okay, we can give it that. I'll draw on my symbols here. So the purple line represents your overall velocity vector. So if you calculated it, that would mean the speed of this race car is 70.7 meters per second at an angle of 45 degrees. So that would be here. But we're not going to calculate that right now. Letter B. So we have a hiker moving 100 meters north and 5,000 meters east in 2 hours. So we want to figure out the hiker's velocity vector in XY format. So essentially what we're going to do is we're going to calculate the velocity in each separate direction. So if he went, how far was it? So if he went 1,000 meters north in 2 hours, right, so say 1,000 meters, right, remember speed is distance over time, so over 2 hours, that equals 500 meters per hour, north, comma, we'll just put north there. Then the other distance was 5,000 meters in 2 hours, right? Because he went both those directions in an accumulated of 2 hours. So that's 2,500 meters per hour. And that was east. All right, so remember east is x and north is y. So essentially we can write that his average velocity in vector format was 2,500, 500 meters per hour, right? So that's his Vx and that's his Vy. Okay? So let's move on to projectile motion, right? That's the big concept here. Oops. Projectile motion. All right, so in your notes, you should have taken notes on this. What is a projectile? Let's change up the color here. Let's go blue. So what is a projectile? So from your notes, you should have seen that a projectile is any object moving through the air that's only affected by gravity, right? So any sports object, lacrosse ball, baseball, soccer ball, football, any types of those things, a bullet, all right? So those things are projectiles, but things like planes, birds, right? Anything that uses another force to keep them in the air, those are not projectiles. So projectiles are only under the force of gravity, assuming air resistance is negligible, okay? When you got things moving at much greater speeds, there is air resistance, but they're still a projectile. That just makes the problem solving much more complicated. So when you have a projectile, so let's go to our handy dandy red circle here. When you have a projectile, the path that it follows, so say we were to launch this red ball through the air, and it would kind of go off the screen over here. So this path is called its trajectory. Probably heard that word before. What's the trajectory of blah, blah, blah? Well, the trajectory is the path, at least in physics. It has some other uses, but in physics, for what we need to know, the trajectory of a projectile is the path it follows through the air. So those of you in Algebra 2 or some higher math, you would recognize this shape, right? That's called a parabola, right? If you haven't gotten to that in algebra, you will soon. That's the shape of this trajectory, or anything in the air. It's either parabola or half parabola. All right, so when we talk about a projectile, right, it goes a certain distance. That's referred to as the range. Okay, so the distance, the distance an object travels through the air horizontally is called its range. Okay, and you would probably be able to guess. Let's erase this here. So that's the horizontal distance. The vertical distance is its height, right? So that's the height. At any point, it could be any point, but a lot of times in these type of problems, we're just concerned with the maximum height, which would be at the peak of the parabola or the trajectory. So the range of a projectile depends mainly upon the speed and the angle at which it's launched. Okay, so this is where the velocity vectors come in. So remember, when you launch something at an angle, it's going to have a horizontal and vertical component to its velocity. So when you launch something at an angle, it will have an initial Vy and an initial Vx. Okay? So these numbers will affect the range. Okay? These numbers will affect the range. So to have a greater range, generally you need to launch something with a greater velocity. But the angle, right, will affect, how far it goes. So, because you could shoot something really fast at a really high angle here. You could shoot something really fast, but it probably won't go that far, right? Because you shot it so high. So later in my talk here, I'll talk about the optimum angle to get the most range. Some of you may already know that. So we consider projectile motion two-dimensional because what? Well, projectile motion is two-dimensional because it has both a horizontal velocity or horizontal motion and vertical motion are happening at the same time. Okay, so they happen at the same time. The key concept here is that Vx, horizontal velocity, and Vy, those two are completely independent. So that means that your vertical velocity has zero effect. Oh, your horizontal velocity has zero effect on your vertical velocity. They act independently of each other. They don't affect each other whatsoever, right? So your x and your y act alone, okay? That is a big, big key here. So the first example, and really the only case we're going to look at here, is projectile launched with zero vertical velocity. So the easiest one to see is a ball rolling off a table. So let's make a little table here. Nice. Cool. All right. So if we have a ball that's rolling, it's rolling off the table. So we're going to give it, we're just going to kind of follow along with the book here, use the book's example. We're going to give it an initial horizontal velocity of 5 meters per second. So that means that's the speed the ball has, right, and direction, because it's horizontal, moving right, the second it leaves the table, right? So it's moving all horizontal, no vertical, so you could write that as 5,0 meters per second. So the key thing to know about projectile motion here in terms of horizontal velocity is that horizontal velocity stays constant. And I'm going to box that. Horizontal velocity stays constant. Springer in the background sneezing. So horizontal velocity stays constant. Why is this though? Why would horizontal velocity stay constant? Well, in the absence of air resistance, okay, in the absence of air resistance, the only force present on the ball, let's see, what color should we use here? Let's use green. The only force present on the ball currently, right, as it leaves the table is gravity, right? So there's only one force acting in the vertical direction. So this gravity force does not affect anything that's going on horizontally. So if there's no force in the horizontal direction, right, go back to Newton's laws, then nothing is going to affect it horizontally, right? It's going to continue its same state of motion horizontally unless something affects it in that direction. So if we had air resistance come into play, then yeah, there would be something affecting its motion, its speed horizontally, but we don't. So our horizontal velocity stays constant, right? And if you go into higher level courses, it will stay constant all the way up until way higher level college physics, because this is only the most basic form of projectile motion right here, just the basic ball rolling off the table. All right, so let's erase some of this stuff here. Okay, so we have this ball rolling off a table. So what's going to happen as this ball continues to roll is that it's going to accelerate downward due to gravity. So the longer it's in the air, the more it's going to accelerate. And the more ground it's going to cover vertically each passing second. So we'll draw here, here, here. Okay, let's get these little dots. All right, so if we draw in our vectors here horizontally, we're going to draw them at about the same length, so about 3.5 here, because the horizontal velocity doesn't change. So the entire time of this projectile's flight, it's moving with the same horizontal speed. But the vertical velocity will increase every second. So let's pick a color for vertical. Let's go with green. All right, so at this first point, it really doesn't move a whole lot vertically because it hasn't had much time to accelerate yet. So it's just going to be a small amount of, if I can get this right, it's not going to let me draw it properly. Oh, there we go. So it's going to have a very small y velocity. Right? But after maybe the second, it's gained a little bit more speed in the y direction. Right? Another second goes by, it's accelerating even faster in the y direction. And then we get another second going by, and its speed is increasing even more in the y direction. Right, and if we could continue down here, we would draw that way down there. Okay, but let's assume it hits the floor. So our purple line here, remember, is our Vx, and our green line is our Vy. All right? So key point of emphasis here, right? The ball is in, this is a concept from earlier, the ball or the projectile, any projectile, going back, this is an old word, is in, technically also in free fall. It is a projectile, but it is in free fall motion, meaning the only force acting on it is gravity, which points down. So your Vy, your vertical velocity, will be constantly accelerated or decelerated if it were moving upwards by gravity. Okay, but whatever your x velocity was, it'll stay the same as long as there's no air resistance. So what is this factor that it increases? Well, if you remember, g, the acceleration of gravity, right, which is, it's g, it's acceleration, so it's a vector. So we can now put that above there, is 9.8 meters per second squared downward. So every second that goes by, your y velocity increases, okay, in speed. Okay, it's pointing down, but it increases in speed by 9.8 meters per second every second. So every second your projectile is in the air, it's either slowing down, okay, if it were moving upwards, or if it's moving downwards, every second it's going to speed up by 9.8 meters per second. Okay? So remember, we had an equation for this. There are free fall motion, but now we have a little bit different way to write it. So our Vy, our vertical velocity, equals g, acceleration due to gravity, times time. All right, so our velocity at any point in the y direction can be figured out by Vy equals gt, g times t. Okay? So rearranging that, if we wanted to figure out the time a projectile was in the air, if we knew this and we knew this, we could figure out the time. So we could rearrange that with algebra and make that t, our time, equals Vy, our vertical velocity, divided by g. Right? So in the x direction, we have, if we want to figure out our x velocity, remember speed is constant in the x direction, so we can just use our regular old a relationship between distance, speed, and time that we learned in the beginning of the year. So our speed in our x direction, our velocity, equals our distance in the x direction divided by time. So if we want to rearrange that to solve for distance, okay, that would simply be simple algebra here. Dx, our distance in the x direction, equals Vx, put a parentheses around there, times time. Okay? So, if we want to find the vertical distance, okay, it's a little bit more of a complicated equation, but we've used it before. But I'm kind of going to give it to you simply here, as in the book. I could do a little bit deeper dive, but given our situation, I don't think that's very necessary. So if you remember before, free fall distance equals 1/2 gt squared, right? So we can break that down simply and write that as distance in the y direction, up and down, equals 4.9. And the reason it's 4.9 is because 1/2 g, like I just wrote, is 1/2 times 9.8, which is 4.9. So it's 4.9 time squared. All right, so that's your vertical distance, and that's your vertical distance, horizontal velocity, horizontal distance, time, okay, and your vertical velocity. Okay? So an important thing to note here, I'm going to write this in red. So these equations, right, are not the end-all be-all, okay? So these equations are only suitable, these only work when your projectile, let's say when object starts with 0 vertical velocity. All right, that's important. If something was launched, like we had in our examples earlier, with an initial vertical velocity, like if you launch something out of a cannon, if you kick a soccer ball up or a football up, or you throw a baseball at an angle upwards, these equations, all right, are not complete. There are larger equations that potentially could take a deeper dive into, but now's not the time. You would see the full equations in an honors or an AP Physics 1 type class. Maybe if we had more time, if we were at school right now, but that's not entirely necessary for this course. So we're only going to be dealing right now with 0 vertical velocity. Okay, so that's what these equations are going to be used for. They're kind of trimmed down a bit. So when you're talking about range, all right, there's a projectile, we get launched. The book uses an example of a golfer, right? We all should know what golf is. When you're hitting golf balls and you want the ball to go as far as possible, how should you want to hit it? All right, so it's not easy to control, but we can control the speed and the angle at which you hit it. Actually, in real life, it's very hard to do that. But if you could control that easily, what angle would you want to hit it to give it the most horizontal distance? So say we have our, can I change that? Yeah, let's go with black here. So if we have our golf ball here, say we hit it directly upwards at 90 degrees. We give it no horizontal velocity. All right, here's our golfer. And there's this, give him a little club here. I'll call it Zach Lavin. All right, this is Zach, ZG, Zach Lavin. Okay, so he somehow manages to hit the golf ball directly upward. This scenario would give the ball the greatest airtime. So this case will give it the greatest airtime, but there is essentially, well, not essentially, but there is zero range. Zero range. It had no horizontal velocity, right? Vx equals 0. So you're not going to get any range if you hit it directly upward, right? But you'll give it the greatest airtime. Okay. So say, well, let's just do it this way. So say we launch something then. So say Zach goes, okay, well, if I hit it at 90 degrees, it gets the greatest airtime. But what if I hit it at 0 degrees? That'll give me the biggest range, right? So say I hit it really hard. Oops. Say I hit it really hard horizontally. Right? At exactly 0 degrees. But what happens? So unless we're on some type of platform, he's on the ground, so that's not the case. So he's on some grass right here. So if he hits it at 0 degrees, that it doesn't go in the air at all. So there's zero air time. So as soon as he hits it, it's already on the ground. So its range is 0 meters. The ball has greatest horizontal velocity, so its Vx is at its max. But it hits the ground right away. So that doesn't give us any range. So our range would equal 0. Okay, so I spelled that wrong. Range equals 0. So what can we do? How can we launch this ball to give it the most range? Okay, so the greatest range you see is at 45 degrees, right? Smack in the middle. So to hit something the farthest, you want to hit it with equal horizontal and vertical velocities. So this will give your ball sufficient airtime and sufficient hang time, or insufficient horizontal velocity for it to continue to go the farthest and maintain that horizontal velocity. All right? So this is halfway between vertical, halfway between horizontal. So your ball would go the farthest. Okay? So what you'll see is different, as some angles will have the same range. So for example, if you hit something at 80 degrees, if you hit something at 80 degrees, so let's say straight up, almost straight up, it would end up having the same range as if you hit something at 10 degrees. So just like right up there, it would end up having the same range. Okay, and that's based on trigonometry, right? So a couple of these different angles, whether it's shallow and steep, they'll end up having the same range. But to get the most range, you need to hit it at 45-degree angle. Okay. So I'm going to do some example problems here. So first things first, we have a stunt driver drives off a cliff with a speed of 20 meters per second. He lands in the lake below 2 seconds later. Okay, so we want to find the range, horizontal distance, and the height of the cliff. Okay, so we are looking for dx for distance in the x direction and dy, distance in the y direction. Given you're given t, right? And you're given Vx. So our equations that we're going to use, our relationships, that we wrote it down earlier, since we are looking for dx, we're going to be using that equation. Dx equals Vx times t. And also, we need our vertical distance. Well, that's going to be dy equals 4.9 t squared. Okay? So to solve that, over here, so our horizontal distance, dx, equals 20 meters per second times 2 seconds. It was in the air for 2 seconds. So he went 40 meters horizontally. Okay, it was in the air 2 seconds, the constant speed of 20 meters per second. Remember, it doesn't change horizontally. So he went 40 meters in the x direction. Dy equals 4.9 t squared. Okay, still he was in the air 2 seconds. Time doesn't have a direction, right? So it moved 2 seconds in the horizontal direction and 2 seconds in the vertical direction, right? As it fell off the cliff, it was just in the air for 2 seconds. So we can use the same time for both. All right, 4.9 times 2 squared, file PEMDAS, blah, blah, blah. Okay, you get a vertical distance of 19.6 meters. Okay, so you kind of see it there. All right, so letter A. Repeat the above problem with a time of 3 seconds instead of 2. So if it was in the air for 3 seconds instead of 2 seconds, let's see how that would affect it. So dx equals Vx times t, just like before. Vx is still 20 meters per second. Our time is 3 seconds now, as per the problem. So that means if that were the case, if it were flying for 3 seconds, it would have traveled 60 meters horizontally. Okay, 60 meters, so 20 more meters. Now our dy, we have 4.9 times 3 seconds squared, right? The equation we used before. That would increase our vertical distance, our height. So if it were in the air for 3 seconds, that means it would have had to have fallen a height of 44.1 meters. Okay? So we're treating these completely separately. All right, next example. Letter B here. You kick a soccer ball and it travels a horizontal distance of 12 meters during the 1.5 seconds in the air. What was the ball's initial horizontal speed? Okay, so let's go over here. We got a red soccer ball, like that. That's an oval. Yeah, that's nice. Okay. We kick the soccer ball, it travels a horizontal distance, so okay, it goes 12 meters. Goes 12 meters. T equals 1.5 seconds. What was the ball's initial horizontal speed? Okay. So we are looking for the x. We are given dx and time. What equation are we going to use? Well, there's only one equation that uses all three of those. That's Vx equals dx times time. Let's solve for it. Vx equals 12 meters. Come on, Mr. Perlstein, use your your units, times 1.5 seconds. And that's going to equal, I made a mistake. made a mistake. So, misremembered the equation for a second there. Vx is dx over t, right? I'm already 45 minutes into this recording. I'm not going to do it again. So, we make mistakes. Vx equals dx over t. So, Vx equals 12 meters divided by 1.5 seconds. That equals 8 meters per second in the x direction. So that means it was hit with 8 meters per second horizontally, and there was still some unknown vertical velocity it was kicked with, but we're not concerned about that because the problem didn't ask for it. So this is from the worksheet that you're going to have some of your homework on. So here are the steps, right? You can see this on your worksheet, but your steps should be as follows to solving these. If you follow these steps, you will be fine. First, you need to read the problem. Diagramming helps on a separate sheet of paper. You need to know what you're given and what you're looking for. Okay, we've been doing that all year. What are we looking for? What are we given? What are the equations? So that's the next step. Determine the equations for vertical motion that I wrote out, or horizontal motion. So which of those will help you solve it? Okay, which takes you back to what do we need to solve for? So you're probably going to need more than one equation, not all the time, but oftentimes projectile motion, a little bit complicated, you might need more than one. So remember, these are your 3 base equations you're working from. You can use algebra to move things around, okay? So in the y direction, remember gravity is included. That's 9.8 meters per second squared, little g. And then note here, Vx is, our initial velocity in the x direction, right? And that's constant, that doesn't change. And note, this is only suitable for situations where the projectile starts with 0 vertical velocity. If the projectile is launched up or down at an angle, the equations are more complicated. So I'll get you guys started here on number 1. All right, so number 1 with a worksheet. This you will have 1 through 7 as your homework. So this is number 1. So we have a cat. Let's draw a cat here, a little stick figure cat. Meow. All right, it's on a roof, and it jumps from one roof to another, which is 5 meters away and 3 meters below. All right, so it is 3 meters below, 5 meters away. So we want to find out the minimum horizontal speed with which the cat must jump off the first roof in order to make it to the second roof. All right, so it's just jumping straight horizontally. Okay, so we are looking for Vx, horizontal speed. Okay, and we are given that, what is it calling? We're given that dx equals 3 meters and back up, dx equals 5 meters, dy equals 3 meters. Our equations, since we're dealing with both x and y, all right, we're going to have dx equals what? What does dx equal? Well, if you look back here, dx equals vertical velocity times time. Dx equals, or not horizontal velocity, Vx times time. We will also need something vertically. So let's go back, let's look at our equations. Well, we don't need our vertical velocity, all right, but we need our vertical distance because we have that, right? So dy equals 4.9 t squared. So, to solve, right, how would we solve that? How would we solve? Well, use what we're given and plug them into the equations. Hint, if you try and do this first, you have two unknowns. There's two things we don't know. We can't use that equation first. So you have to use this first to solve for t squared. And remember, to solve for something algebraically with the square root, and I'll do it for you off to the right, you need to, with a square, you need to use a square root, okay? So that would look, right, if we divided 4.9 to both sides, you had t squared by itself, we would need to take the square root of both sides, right? So that's essentially how you go about starting that problem. Then you need to use your time and plug it back into your x equation to get your vertical or horizontal speed. Okay, so that's number one. We're going to have 1 through 7 for homework, most on Go Formative. Okay, you're going to have that on Go Formative. All right.